Hi, everyone. I'm going to talk about locally testable codes that get the C-cubed property, constant rate, constant distance, and constant locality, which means it's locally testable with a constant number of queries. This is work that is joint with Shai Evra, Ron Livne, Alex Lubotzky, and Shahar Mozes. Okay, so we're talking here about error-correcting codes, which are just linear subspaces of 0, 1 to the n. Could be over larger alphabets, but for today, let's focus on 0 and 1. So we have a linear subspace, and the property of an error-correcting code is that all the points in the subspace are far from each other in Hamming distance. The points, the strings, the elements in the subspace are called code words. And we think of the usefulness of this is that we might imagine sending a code word over a noisy channel and some of the bits get flipped. Therefore, if we know in advance, we prepared the code in the way that pairwise distinct code words are far away, they have many bits that are different, then if you know that only a few bits got flipped, there's going to be a unique way to recover the code word. The parameter that is in charge of this is called the distance parameter, and it's the minimum distance between two different code words. So we take the minimum over all pairs xy in the code, and you measure how many coordinates xi is different from yi, and we normalize by n. So it's a number between 0 and 1. Of course, we want to have many code words in our code, and that's measured by the rate. So we want to pack as many points into this space as possible. And the rate measures how many points did we pack in. And we measure this by taking the dimension of the linear subspace, which is log the number of actual points, divided by n, which is the ambient dimension. So the maximum number of code words would be 2 to the n, but then they would be not so far apart. And the golden standard is to have both the distance be a constant and the rate be a constant. So let's talk a little bit about local testability. Rate and distance have been studied for decades and decades. They are really like the central objects in any error-correcting code. Local testability is a much newer kind of phenomenon. You can date it back to the beginning of the PCP, so maybe 30 years or so. And the main question here is, given a string, n-bit string, is it in a given specified subspace C, which in our case is this code? This is a property testing question, and the idea of local testability is that we want to be able to decide this question by reading only a small part of W and not having to read the entire thing. A code is defined to be locally testable with Q queries if there is a tester, T, that has query access, or sometimes people say oracle access, to a given word W. It reads Q randomized bits from W, so it selects where to read at random, and then it says accept or reject. And we know that if W was indeed in the code, the acceptance probability would be 1. So the code words will actually always be accepted. And we want to say that if W is not in the code, then we always reject. But that's too much to ask because we're only reading a tiny portion of W. So if someone flipped a random bit somewhere, we're not going to catch it. So the best thing we can hope for is that we're going to catch W not being in C with probability that's proportional to how many bits got flipped. So we're going to measure here on the right, we measure the distance of W from the code. And we want this to be a lower bound to the probability of rejection. That's kind of being a strong locally testable code. And the number of bits that the tester reads, Q, is the locality of the tester. And if we manage to get something like that, then our code is called a locally testable code. So really, if I want to think about locally testable codes, it's interesting to understand that there are two measures of distance of a given word from the code. Let's look into that for a minute. So suppose we have a code that's defined by some linear constraints. And in our setting, the constraints are always going to be low density or sparse. So each constraint only looks at a few bits. Okay, so you have a bunch of linear constraints. Each one of them is very sparse. So we can call them local constraints or local tests. So many linear subspaces can be defined this way. Now, if we have a string W, we can measure how far W is from the code in two ways. The classical way is just the Hamming distance. What's the smallest number of bits that you need to flip to make W reside inside the subspace? That's a very well-known measure, but it's not so easy to calculate, right? If I give you a string and a definition of a subspace, a priori, you might need an exponential amount of time to find out what's the smallest number of changes you need to make. The second kind of distance, let me call it here the T distance, has to do with a specific set of linear constraints, T1 after Tm. And it's just asking how many of the linear constraints are violated by W. Maybe W is almost in the subspace in the sense that it satisfies almost all of the linear constraints, but maybe it violates a few of them. And actually notice that the T distance is something that's easy to calculate, right? You could certainly do it in polynomial time. And you can get a good estimate of this distance by just selecting a random I from 1 to m and calculating Ti. As we said, all the Ti's are sparse, so to calculate whether W violates Ti or not is going to cost you only a small number of bits that you read from W. Okay, so we have these two distances. The Hamming distance is natural, but might be hard to compute. And the T distance is easy to compute or to estimate. What is the relationship between these two distances? An LTC, another way to define an LTC, it's a code, a subspace, where these two distances are good estimates of one another. The T distance will give you a good estimate for the Hamming distance. Okay? So I also added here that the T distance is local because you can also define an error correcting code with a bunch of not sparse constraints, but then it will be much easier to get an LTC. The trick is to have the T distance be defined over a set of sparse constraints, and yet have it be a good estimate for the Hamming distance. And you can think that this might be very useful, right? Because when we use error correcting codes in communication, we might, decoding might be kind of costly, and we can, while we receive a word, we can just test if many errors happened, and if so, not bother with decoding, just ask for a retransmission. Okay, so I'm not going to spend time on the historical background. You can pause the video and look at this. Just to say that LTCs came up from the PCP literature, property testing, and this has been an open question that in recent years, with the rise of the ideas in high-dimensional expanders, it seems like we might get close to getting such LTCs. Okay, so what is our main result? Our main result is that for every R, for every rate parameter between 0 and 1, there exists some other delta and a number Q, which is the number of queries, and an explicit construction of a locally testable code, an error correcting code with rate R, distance delta, and locally testable with Q queries. In fact, relying on previous works, once you have this result, you can use some concatenation ideas and amplification to get locally testable codes for every pair of R and delta that approach the Gilbert-Farsham bound. So for every parameters R and delta for which we know that error correcting codes exist, we now know that locally testable error correcting codes exist. Let me also add that this transformation is randomized. So it's a nice question to figure out if we can approach the GV bound with a construction that's actually explicit. Let me also mention a second paper that's presented in this conference by Pantelev and Kalachev, which is really a beautiful result, showing not only they showed an almost identical construction. They look at it from a different point of view, and they construct both quantum LDPC codes and local testable codes like we do. So they show basically that the same construction gives both objects, and you will hear about it in their talk. Okay, so we're gonna first talk about expander codes that date back to maybe 25 years ago, and of Sipser and Spielman. Then we'll show kind of second level above regular expanders, which we're going to call a graph with squares. It's like kind of a second dimension. And then we're going to define the code and talk about its properties just a tiny bit. Okay, so what are expander codes? These are codes constructed by Sipser and Spielman, and they're really a very simple and beautiful idea. They say the following thing: if I already have a small base code, C0, on a constant number of bits, say let's call it D, and if I also have a D-regular expander graph that has very good expansion, and I'm not going to talk exactly about what expansion is, just to say that it's a graph that's, even though every vertex has only D edges coming out of it, it's a highly connected graph. So if I have these two objects, an expander and a good base code, then I can construct out of it a code. And in my new code, the strings in the code are going to be functions labeling the edges with 0 and 1. So we started with a code on D bits, we get a code on E bits, where E is the number of edges. It can be huge. And the constraints of the code are very simple. Around every vertex, I look at all the bits of the edges around that vertex, and I want this little D-bit string to belong to the base code C0. So that's the definition of the Sipser-Spielman codes, and they proved that these codes have a constant relative distance and constant rate, and they can be decoded in linear time. And these codes can actually be viewed as Tanner codes. Tanner described the whole scheme of constructing codes by looking at a bipartite graph and putting the bits on the left side of on the left vertices. So in his codes, the elements in the code will be strings labeling the left-hand side. And on the right-hand side, he's going to put, for every right-hand vertex, he's going to think of the vertices touching this vertex as needing to be inside the code C0. So that's the general Tanner code scheme. And the Sipser-Spielman codes are a kind of Tanner code, where you put your bipartite graph that you choose is the edge vertex incidence graph. So notice here on the bottom, I wrote that our bipartite graph connects the bits are put on the edges and they're connected to the vertices. Sometimes this is called the factor graph. In our codes, we're also going to be able to describe them as a Tanner code, but in our codes, the bits are no longer going to be on the edges. Rather, we're going to also have squares. So we're going to have vertices, edges, and squares, which are basically 4 cycles in our graph. And the bits are now going to be on the squares. So we'll see this. Okay, so first, let's start by describing this new object, which we call a left-right Cayley complex. It's like a Cayley graph with a second level. It's a graph with vertices, edges, and also squares. So we start with a finite group G, and we're going to also take a set of generators A that's closed under taking inverses, so that if A is in our set, also A inverse is in our set. And the Cayley graph of G with respect to generator set A is the graph that has a vertex for every element in G, and the edges are for all the generators. So you connect G to A times G for every generator A. And this graph is undirected because if G goes to AG, then AG goes to A inverse times AG, which is G. So that's a standard Cayley graph. And we're going to actually take two Cayley graphs, one with the generating set A and one with the generating set B. But we're going to do it with a little twist. The A graph is going to use left multiplication. So the A edges go from G to A times G. And the B graph is going to use right multiplication. So G is going to G times B. Okay. And you have this graph where you have two sets of edges on the same set of vertices. But now you see here in the picture that there are squares. So who are the squares? Well, notice that for an element of the group G and two generators A and B, you can move from G through a blue edge to A times G. And you can also move through a red edge to G times B. Okay, but if you moved through a red edge to G times B, then you can take the blue edge and move to A times GB. And you can also reach AGB through the other path, first taking the blue edge to AG and then taking the red edge to AG times B. So you get a square. Now, of course, you can see that this square, as we looked at it from G, from the point of view of G, as like the root. Of course, we can look at different vertices as the roots. So each square can really have 4 different roots, right? For example, I can look at the top vertex, AGB, think of it as the root, and then with A inverse, I move to the left neighbor, and with B inverse, I move to the right neighbor, or to the blue neighbor. Okay, so this triple A inverse, AGB, B inverse describes the same square from a different root. So if I want to discuss unrooted squares, I'm going to identify these 4 different triples as one equivalence class. Okay, so a rooted square is just a triple AGB, and an unrooted square is this equivalence class. Okay, we're going to only talk about unrooted squares. And we're going to look at the incidence relation. So a square naturally contains 4 edges, right? The edge from G to AG, the edge from G to GB, and so on. And also the 4 vertices, G, AG, GB, and so on. And the set of squares, so we have our graph, we have the vertices and edges, that's easy. The new thing is to look at this set of squares, which is the collection of equivalence classes, square brackets, AGB. Okay, so let's kind of summarize what is the left-right Cayley complex. You see it's a very simple object. You start with a finite group G and 2 sets of generators, A and B, that are closed under inverses. And you define the left-right Cayley complex as having vertices G, edges, the A edges with left multiplication, B edges with right multiplication, and the squares, which are the equivalence classes of the rooted squares. We're going to also say that this left-right Cayley complex is a lambda expander if each of the Cayley graphs, GA and GB, each of them is itself a lambda expander. I haven't defined what this is, the standard notion. Lambda is an upper bound on the second eigenvalue of the normalized adjacency matrix of the graph. And of course, it's a well-known theorem that we have explicit constructions. So for any lambda, even as small as we want, there is an explicit, many explicit families of bounded degree Cayley graphs, which will give us bounded degree left-right complexes. So now I want to move to look at the structure of this Cayley complex, kind of zooming into the local structure. What's going on in a local neighborhood of an edge or a vertex? So let's start with an edge. Suppose we look at the edge from G to AG. And who are the possible squares that touch this edge? They're naturally identified with elements of B. As you can see, for every element B, I can move from G to GB1, and also from AG to AGB1. But then GB1 and AGB1 will also have an edge between them. This edge is parallel to the edge we started with, and it's an A edge. Okay, so for every element of B, I have a square. And really what I have here is a book whose spine is this edge from G to AG. Similarly, for an edge in the right direction, in the B direction, an edge from G to GB, the squares around it are identified with the elements of A. For every A, for example, A3, I can move from G to A3 times G, and I can also move from GB to A3 times GB. And this edge will close here with B. So we have here around every edge, we have this book of whose pages are the squares. And notice that each square, since it touches 4 edges, it's like a book that has 4 different spines. You can open it this way or that way or that way. So you can think of this picture, thanks to the Simons Institute and their graphics designer for drawing it, where all the squares are kind of touching many other squares. Moving on to looking at the neighborhood of a vertex corresponds to a group element G, and it has how many neighbors? It has A plus B different neighbors, cardinality of A plus cardinality of B. And for every choice of little a from A and little b from B, there's going to be a square touching G, right? So we naturally have this, well, I want to say bijection, but it's not always going to be a bijection, but definitely going to be an onto map, mapping every pair of AB to a square. So now I described the Cayley complex, and I'm going to move on to describe the code itself. So suppose we have a left-right Cayley complex, and let me also take as building blocks a base code, just like Sipser and Spielmann had their C0, I'm going to also have a C0. And if I assume, for example, that A and B, they can even be the same set for simplicity, I can take A equals B, and I'll take just CA and CB to both equal some specific base code C0. And now I can define my code to be all the strings, all the functions that give a bit to every square. So I put bits on the squares. And what I require is that when I look at an edge and I look at all the squares around this edge, and I look at this D-bit string, it's in C0. Very much analogously to the Sipser and Spielmann expander code. So formally, the code is just a collection of all functions from the squares to 0, 1, such that for every G and B, so I'm looking really at the edge from G to GB, when I range over the A's, I get a string, and this string is in CA. And if I fix A and G, so it's an edge from G to AG, when I range over the B's, I'm in CB. So this is a one-line definition of the code. Now, what are the properties of the code? So I'm not going to spend too much time because the lecture is short. It's not hard to convince yourself that if R0 is the rate of the base code CA or NCB, then the entire rate of our code is at least 4R0 minus 3. And the way we show this is just by counting how many degrees of freedom we have, that's the number of squares, and how many linear constraints we have. And the constraints might be dependent, but even if they were all independent, that's the rate that we would get. What about the distance? So how did Sipser and Spielmann prove that their codes had a constant relative distance? They relied on a propagation argument. They essentially showed that if you have a non-zero code word, so let me try to do it on our code. If you have a non-zero code word, so there is some square that has a 1, then around any one of the edges touching that square, you should see a code word of C0, of C0. And this code word has a 1, so itself it's non-zero. So there are many other squares that are 1s. Okay, so a single 1 already caused some more 1s. And if you go to each one of these squares, they force more squares to be 1. And you start kind of walking in this graph from square to square, from square to square. And since we assumed some information about the expansion of this graph, we can deduce using kind of standard expansion arguments that the number of ones must be huge. It's a linear fraction. What other properties does our code have? So key properties that the local views are, in fact, interesting little intermediate codes, which are tensor codes. And that's a key property because the tensor codes themselves are locally testable. And we're going to use this to kind of lift the small local testability to local testability of the entire code. So why are we saying this? The local views are tensor codes. Let's look at the specific vertex G. Okay? And let's fix some code word F. So F is a code word on the entire set of squares, and we look at it just around just on the squares around a specific vertex G. And how does it look like? Okay, so we just look at F on the squares dot G dot. Okay, and the point is that, let me go back one. Yeah, the point is I copied here in the bottom the definition of the code. And in the definition of the code, it says that if you put B, you fix B and you let A range freely, so that's like looking at the edge from G to GB and looking at all the squares of the form A1, GB, A2, GB, and so on, then this whole set of squares must be in CA. Now in this picture, this set of squares is just a column here. This orange column needs to be in CA. And that's true for each one of the columns, right? Because it's true for every B. So you see that in this table, all the columns need to belong to CA. And very similarly, if you fix A, it's like fixing a row here, and you let B range in capital B, then you're really looking at a row in this table. And this row, by definition of the code, needs to be in CB. So what you get is that the table of squares touching G satisfies that all the rows are in CB and all the columns are in CA. That's actually the definition of a tensor code. So we have this property that all the local views are tensor codes. And our theorem says that if you start with a Cayley, left-right Cayley complex that's a lambda expander, and if the local tensor code CA tensor CB has some local testability property, then assuming some of the parameters align correctly, which is very easy to make sure that this happens, you get that the entire code is locally testable. And how would you test the code? The tester is actually very easy. You select a vertex uniformly at random, and you look at the entire neighborhood of the vertex. You look at all the A times B squares, that's a small number of squares, that touch G, this vertex, and you test that the word there looks like a tensor code word. And the main thing to prove is that the fraction of times, the fraction of vertices G, where this test fails, where the local view is not a valid tensor code word, is an upper bound on the distance of F from the code. So if you see just a little bit amount of failures, it means that your code word can be corrected to be perfect. You might think that that's always the case, but actually it's not true. In an expander code, it could be the case that someone just violates one single constraint, and yet the entire string is very, very, very far from the code. So you have to think about it. Okay, so I guess I'm done with this short talk. Some interesting questions is, these are locally testable codes. Initially, people considered LTCs as components of PCPs. It would be amazing to be able to construct PCPs with good linear parameters, or even just along these lines. And another question is whether these codes can be made practical, what kind of uses can be found for them. All right, thank you so much.